For Lab 2, we looked at the motion of an object falling somewhat slowly that was dropped from rest. In this lab, we seek to find a model for what we observed. We want to find a good model so that we can know what kind of forces from the surroundings are affecting the falling object and its motion. First, we will look at the observed data that we got from Tracker. Then we'll see how we can use the fundamental Newton's second law to create two models of the object's motion using GlowScript. Then we'll compare the models with the original data. The first model will be just gravitational force, and the second will have gravity plus drag force. Finally, we will discuss terminal velocity. We got our initial conditions from Tracker. At time equals 0 seconds, the position of the crumpled paper is set to the origin. And since the ball is starting from rest in my hand, the initial velocity is also 0. Now we can use Newton's second law to construct computer models. Newton's second law gives us the equation final velocity is equal to the initial velocity plus net force over mass times the change in time. When the object is falling, the velocity is changing. This means that the change in velocity is not 0, and that suggests that F net is not 0 also. So there has to be at least one agent in the surroundings that's exerting an influence on the system, and one of these forces comes from the Earth. Weight force is equal to the negative mass times Earth's gravitational constant times j hat. We will first try a model where weight force is the only force acting on the system. And as you can see, although the initial predictions of this model are correct, towards the end, the model and observation are at completely different positions. This is because when the crumpled paper falls down, another force called drag force acts in the opposite direction of the object's motion. Its magnitude is proportional to the square of the object's speed, so that drag force is equal to some constant b, which depends on the properties of the object and its surroundings, times the square of the magnitudes of the velocity times the negative unit vector of velocity. So if we look at Newton's second law again, instead of F net just being equal to weight, F net is equal to weight force plus drag force. B was chosen so that the final position of the model was close to the observed final position. Now, as you can see, this model with gravity and drag force predicts the motion of the object much better than just gravity. But it's not perfect, and this can be because of video distortion or because when using Tracker, the object appeared as a blur, which made it hard to pin its real position. For better results in the future, we can use a special high-speed camera and maybe reduce the video distortion with a tripod. So, which of the two models predicted a terminal velocity? Well, terminal velocity happens when the magnitude of the drag force pointing up becomes the same as the magnitude of the gravitational force. This means that at terminal velocity, F net will equal 0 and the velocity will be constant. However, in the gravity-only model, the velocity will keep changing with the acceleration of gravity that is in one direction. F net will therefore not equal 0 since there is only one force pointing down. But with the gravity plus drag force model, we will see a terminal velocity because drag force that is proportional to velocity squared will eventually balance out the gravitational force. And if you want to see the animation of these arrows, check out the link to the code in the description below. Now, what if we threw the object downward? Would the terminal velocity be the same or different from being dropped at rest? Terminal velocity is not dependent on the initial velocity. It is, however, dependent on the properties of the object itself, like the mass and surface area, and also the gravitational acceleration. So, no matter the initial velocity of the object's terminal velocity will remain the same. We can see this by changing the initial velocity to some negative value in the computer model. And as you can see, both approach the same terminal velocity, which is around negative 3.3.